Okay, let's consider a free body diagramming problem that involves a little bit of trigonometry. A child on a sled is pulled across a horizontal snowy surface at constant velocity. The applied force is 22 newtons at an angle of 30 degrees with respect to the horizontal. If the child and sled have a combined mass of 18.5 kilograms, part A, what is the normal force acting on the sled? And part B, what is the friction force acting on the sled? I was really nice in this video. I've already included what a free body diagram might look like in a coordinate system. The picture shows that we have an applied force being applied at an angle of 30 degrees with respect to the horizontal. It's very important that you know there is a vertical component to that applied force, and there is a horizontal component to that applied force. To find the vertical component, we could use the sine of 30 degrees times the applied force, and to find the horizontal component of the applied force, multiply the applied force by the cosine of 30 degrees. When we do this problem, we'll make sure that that vertical component of the applied force is factored into the sum of the vertical components for this situation, and we'll make sure that the horizontal component of that applied force is factored into the sum of the horizontal components of this situation. Other forces acting, we have a normal force oriented in the positive y direction, we have a weight force oriented in the negative y direction, and of course, friction always opposes motion. And because in this picture the sled is moving in the positive x direction, friction must act in the negative x direction. Let's start off by solving part A. What is the normal force acting on the sled? If we want to solve the normal force, we need to focus on the forces acting in the vertical direction. Let's start off by writing the sum of the vertical forces. In the vertical direction, the applied force has a vertical component of F sub A times the sine of 30 degrees. That component is a positive component because that is a first quadrant vector. It is oriented north of east, and make sure you remember, if the vector has a northern orientation, its y component is positive. Other forces we're dealing with, we have a normal force oriented in the positive y direction, and we have a weight force oriented in the negative y direction. And by rule of Newton's second law, we will set the sum of those forces equal to ma sub y. There are two very important words in the problem description. You may have run across them: constant velocity. Whenever we're dealing with constant velocity situations, you need to recognize that the acceleration will be zero in both the vertical and the horizontal direction. So my ma sub y term can be rewritten as simply 0 in this situation. And because the weight force is defined as mass times gravity, I will rewrite this equation just one more time. And if you stop and take a look at where we're at, I know the applied force. It was given me in the problem as 22 newtons. I've already taken care of the sine of the angle, which is the sine of 30 degrees. I'm solving for normal force, so we know that's going to be the unknown. I know the mass of the sled, that's 18.5 kilograms, and g is 9.8 meters per second squared here on Earth. We are now ready to solve this thing. Personally, I don't like to plug the numbers in just yet. I'm going to add the mg term to both sides of the equation, and I'm going to subtract f sub a sine 30 from both sides to get f sub n by itself. Now would be a good time to substitute in all the values. And if you have a calculator handy, go ahead and crunch these numbers, and you should get the normal force to equal about 170 newtons. Okay, on to part B. What is the friction force acting on the sled? If we want to calculate the frictional force, we need to focus on the forces acting in the horizontal direction. We have F sub A cosine of 30 acting in the positive horizontal direction, and we have the friction force acting in the negative horizontal direction. Those are the only two forces acting in the horizontal direction, so let's go ahead and write the sum of the horizontal forces. Shown on the screen is the sum of the horizontal forces. We have the applied force times the cosine of 30 degrees minus the frictional force equals ma sub x. In this situation, we are dealing with translational equilibrium, meaning that ma sub x will equal 0. Again, the key words were constant velocity. So because I'm running a little bit out of space, I'm going to do two steps at once. I know ma sub x is 0, and I want to solve for frictional force, so I'm going to add the frictional force to both sides of this equation to get the frictional force by itself. The frictional force is equal to the applied force multiplied by the cosine of 30 degrees. The applied force in this problem was 22 newtons, so all you have to do is take 22 newtons times the cosine of 30, and you get an answer. You should get the frictional force to be about 19 newtons. If you need to pause the video and take a look at all this, please feel free to do so, because on the next slide, I'm going to put you to the test and see if you know how to solve a problem very similar to this. Okay, what I'd like you to do is pause the video at this point and try out the problem that you see on the screen. It's basically the same situation that we dealt with in the last problem, but now there is a horizontal acceleration of 0.85 meters per second squared. So that means as the child's being pulled, her velocity will increase because there is acceleration in the horizontal direction. Once you finish this problem, go ahead and hit play, and on the screen you'll see all of my work that I've shown to solve this problem. Although I won't have time to go over all the work in explicit detail, hopefully all the work shown provides you a really good way to check your answer. Okay, hopefully you had a chance to solve this problem. Your answer to part A should have been the exact same answer as for the first problem we looked at. The normal force is 170 newtons. And in part B, because there is acceleration in this situation, but the mass of the sled didn't change, and the applied force and the angle didn't change, the frictional force has to be much less in this situation if the sled is going to accelerate in the positive direction. This answer of about 3.3 newtons is getting pretty close to frictionless, but given the information in this problem, the surface has to be nearly frictionless for the sled to be accelerating in the positive x direction with an applied force of just 22 newtons at an angle of 30 degrees with respect to the horizontal. If you need to pause the video and take a look at my work, please do so. Hopefully you were able to get those two answers. Okay, thanks for watching. In the next episode, we'll look at a simple frictionless inclined plane example. And in class, we'll have plenty of practice with problem-solving situations very similar to those that you just encountered.